Hey everyone, welcome back. Today we'll solve one of the classic computer science problems, longest increasing subsequence, Leetcode 300. This problem is part of Blind 75, a curated list of essential coding interview questions. You can find the full list linked in the description below. Be sure to check it out. Now to the problem. In this problem, we are given an integer array nums and we have to return the length of the longest increasing subsequence, which means every element in the sequence should be greater than 1 before it, and the subsequence does not need to be contiguous. However, the elements must maintain the relative order compared to the original array. For example, if the original array was 1, 2, 3, 4, 5, then 135 can be a valid subsequence, because even though it does not have elements like 2 and 4, all the remaining elements in the subsequence are in the same relative order as they are in the original array. Then in example 1, for the given nums array, one of the longest increasing subsequence can be 2, 5, 7, 101. So if we take up 5, we cannot take 3 because the sequence must strictly increase. Elements cannot decrease or dip in an increasing sequence. Or we can skip 5 and take 3 instead, which is more than the previous element 2. And now the subsequence will be 2, 3, 7, 101. Similarly, we can skip 101 and take 18 instead, but we have to return the length of the longest increasing subsequence, which will be 4. Similarly, in example 2, for the given nums array, one of the longest increasing subsequence can be 0, 1, 2 and 3, which has length equal to 4, and that will be our answer. And finally, in example 3, all the elements are equal, so the length of the longest subsequence will be 1 in this case. Now in terms of solution, one of the naive approach can be to explore all possible subsequences of the given array and check if they are increasing. Among these increasing subsequences, we can return the length of the longest one. So we start subsequences at each index of the array, starting with index 0, and recursively build subsequences by deciding whether to include the current element in the subsequence or skip the element and move to the next one. At each step, we check if the current element can extend the previous element to form an increasing subsequence. So, for each recursive call, we will use the current index and the index or value of the last included element in the subsequence. Here, for example, we start at index 0 and previous element is not set. So, we can treat it like a negative infinity. Now, we can include 10 or skip it. And if we include 10, then we move to the next index and the previous element becomes 10. And here including 10 makes sense because that increases the length of the increasing subsequence to 1. Now again for the current index, we can either include 9 or exclude it. Now if we try to include 9, it will result in a decreasing sequence. Hence we hit the dead end here. So let's proceed by skipping 9 and moving to the next index, which is 2. Now the previous element is still 10. But the current element is 2. Again, we will try to include 2 or exclude it. And if we try to include it, again it will result in the decreasing sequence. So we skip it and come to index 3. And same will be the case for 5, 3 and 7. Because all these elements are less than 10. And eventually we will come to index 6 where we find element 101. And again we can include 101 or exclude it. So if we include it, this time this is a valid sequence and the length of this sequence is 2. Next, again we move to the next index and see the element 18, and we can either include it or exclude it. If we include it, then it will again result in decreasing sequence because 18 is less than the previous element 101. And if we exclude it, we come to the end of the string and backtrack and come to this path where we skip 101 and the previous element is 10. Now again we include 18 or skip it. If we include it, it will again result in the increasing sequence of length 2, and then we backtrack because now we are at the end of the string. Similarly, if we skip it, we again come to the end of the string and backtrack. Now let's see what happens when we skip 10 and eventually find the length of longest increasing subsequence. Let's get rid of this tree to make some space and move the index back to 9 because we have just skipped 10. And again for 9, we will have two possible choices, either to include 9 or exclude it. And we know that if we include 9, we will again find the length of the longest increasing subsequence starting with 9 will be 2. It will be either the sequence 9 and 101 or 9 and 18. So let's skip that path as well and go to the path where we skip 9 and come to index 2 because that is an interesting index. And again, we have two possibilities whether to include 2 or exclude it. And if we include 2, we move to the next index where we see element 5 and again we will have two possible choices whether to include it or exclude it. And again move to the next possible index where we see element 3. Now if we include 5, the previous element will be 5 and the length of the longest increasing subsequence or LIS starting at index 2 is 2. And again we will have two possible choices whether to include 3 or skip it. And if we include 3, again we will have a decreasing sequence. Hence we will skip it and backtrack and come to the path where we skip it and go to the next index which is 7. And again we can include 7 or skip it. And if we include 7, it is still a valid increasing sequence with elements 2, 5 and 7. And the length of this sequence is 3. And now that we have included it, we go to the next element which is 101. And again we will have two possible choices whether to include it or skip it. And if we include it, this is still a valid increasing sequence and its length is 4. And we go to the next index. And again we will have two possibilities whether to include 18 or skip it. And if we include it, again it will lead to decreasing sequence. So we will backtrack and come to the path where we skip it. And here we are at the end of the array. So we will backtrack and continue with the recursion in the remaining paths. And eventually the length of the longest increasing subsequence will be 4 coming from multiple recursive paths such as this one. Now the time complexity of this approach is O of 2 to the power of n, where n is number of elements in the array. Because for each element in the array, we have two possible choices whether to include it or exclude it. And this results in the recursion tree of depth n. Hence, the overall time complexity is O of 2 to the power of n. And the space complexity will be O of n, again coming from the depth of the recursion. And by now, you may have noticed that the naive solution involves repeating subproblems. For example, length of the longest increasing subsequence, LIS, starting at index say 3 with this element 5 will always be the same whether we start from it as the first element or we pick it after including the element 2. The result of the LIS starting at index 3 doesn't change, it will always be 3, say with elements 5, 7 and 101 or 5, 7 and 18. These repetitive calculations make the naive approach inefficient. So to avoid these redundant calculations, we can use caching or memoization to store the result of each subproblem associated with a given index and the previous element so that it can be reused later without recomputation. So for any given index, we store the length of the LIS for that subproblem and store it. Now the time complexity reduces to O of n square because now for each index, we calculate the length of the longest increasing subsequence starting at that index, and we have to do this for all the n previous elements. Hence the overall time complexity will be O of n square and the space complexity will be O of n square as well because we are using cache storage for n indices and n previous elements resulting in O of n square space, and we are also using the recursion stack which takes O of n space. So the overall space complexity is now O of n square. Now, after understanding the top-down dynamic programming approach with memoization, let's explore the bottom-up method, which eliminates the recursion overhead and builds the solution iteratively. Here we start with the smallest subproblem first and use their results to solve the larger ones. We store the intermediate results in the DP table, where DPI represents the length of the longest increasing subsequence, LIS, that ends at the index I. Initially, all the values in this DP array are set to 1 because every element forms an increasing subsequence of length 1 by itself. Now, similar to the top-down DP approach where we use previous and current indices, here we can use two iterators, I and j, where I points to the current element being considered and j checks all the previous elements before the current element at I. For example, we initially set I at index 1 and j at index 0 to begin checking all possible LIS that can end at index I with a length of 2 or more. And for each pair of indices I and j, we will ask the question, which is whether nums of I is greater than nums of j. Here, for example, the answer is no. But if the answer is yes, then wouldn't it be better to include the nums I in the sequence and ending the LIS at I, as by doing so, we increase the length of the LIS by 1. And to ensure we keep track of the maximum length of LIS ending at index I, we can use the recurrence relation where dp of I is equal to maximum of existing dp of I and dp of j plus 1. This calculation guarantees that dpi contains the maximum length of any increasing subsequence ending at nums I. And finally, our answer will be the largest value in the dp table, which represents the length of the longest increasing subsequence across the entire array. Let's quickly see this in action. Initially, I is at index 1 and j is at index 0. And we check if nums I, that is 9, is greater than nums j. And since 9 is less than 10, we cannot form the increasing sequence. So dp of I, that is dp of 1, stays 1 only. Then we move I to index 2 and check if element 2 can be included to form any of the increasing subsequence. So we compare nums I with nums j, that is 2 with element 10, but since 2 is less than 10, we cannot form the increasing sequence. So we move j to index 1 and again compare 2 with element 9, and again we cannot form an increasing subsequence. So dp of 2 stays 1 itself. Now we move I to index 3 and again compare all the elements before it, which are 10, 9 and 2. And since element 5 is less than both 10 and 9, it will not form the increasing sequence with them. And eventually j comes to index 2, where we compare element 2 with 5 and again ask the same question, is nums I greater than nums j? And this time the answer is yes. And since 5 is more than 2, wouldn't it make sense to include 5 in the subsequence, creating a longer increasing sequence that ends at index 3? So the length of this increasing subsequence will be 1 plus dp of j, which is equal to 1 plus 1 equal to 2. And since it is more than the current value at dp of I, we will set dp of 3 equal to 2 and move I forward to index 4 and again compare all the elements before it. So again for element 3, elements 10 and 9 are more than 5. So LIS cannot be formed. Then we come to index 2 where we see element 2 which is less than 3. So we update dp of 4 to maximum of the current value, that is 1, and dp ending at index 4 including element 2 which is 1 plus 1 equal to 2. And then we move the j pointer forward and compare element 3 with element 5, and since 3 is less than 5, we cannot form the increasing sequence. So it will result in dp of 4 as 1, but it is less than the current dp value which is 2. And now since we have compared all the elements before 3, we will move the I pointer forward and come to element 7 and compare all the elements before it. Now since again 10 and 9 are more than 7, we cannot form the increasing subsequence. So dp of 5 stays 1. Then we move j to index 2 where element is 2, and since it is less than 7, we form the LIS of length 2. Then we move j to index 3 and compare it with element 5, and since 5 is less than 7, we can again form an increasing subsequence. So length of this subsequence will be dp at index 3 plus 1, which is equal to 3. And logically thinking, the sequence will be 2, 5 and 7, where we extended the previous sequence ending at j to also include the number at I. Then we move j pointer forward and compare element 7 with 3. And since 3 is less than 7, again we can form a subsequence which will be of length 3. So dp of 5 remains 3. And now since we have compared all the elements before 7, we will move the I pointer forward and again compare all the elements before it. Now since 10 is less than 101, we increase the length of the LIS, that is dp of 6 to 1 plus dp of 0, which is equal to 2, and move j to index 1. And since again 9 is less than 101, this will also result in an increasing sequence. Hence we will get length of LIS is 2. So dp of 6 stays 2. Then we move j to index 2 where element 2 is also less than 101, and hence will result in dp of length 2. So dp of 6 stays 2, and then we move j to index 3, where since the element 5 is less than 101, dp of 6 becomes 1 plus dp of 3, which is equal to 3. And again we move j pointer forward and come to index 4, and since 3 is less than 101, we will get the corresponding LIS of length 3. So dp of 6 stays 3. Then we move j to index 5, and since again 7 is less than 101, the length of the LIS ending at index 6, that is dp of 6, now becomes dp of 5 plus 1 equal to 4. And now since we are done with all the elements before I, we move the I pointer forward and again compare all the elements before it, which if you follow a similar process will result in dp of 7 as 4. Now since maximum value in this dp table is 4, the length of any LIS will be equal to 4. For example, ones ending at index 6 or 7. Now the time complexity of this approach is O of n square, because for each element I in the array, we iterate through all the previous elements j to determine the value of dp of I. Hence the time complexity is O of n square because of the nested loops. And the space complexity will be O of n to store the results in the dp array of size n. Here is a quick code walkthrough of the algorithm we just talked about, with Java code on left and Python on right. First, let's get the length of the input array and let it be n, and create a dp array of size n, where dpi stores the length of the longest increasing subsequence that ends with nums I. Initially, all the elements in the dp array will be equal to 1, because every single element can at a minimum form an increasing subsequence of length 1. Let's also initialize answer to 0. This variable will keep track of the maximum LIS found across all elements in the dp table. Now we will start iteration on the array using two pointers I and j, where the outer loop I goes from 0 to n minus 1 and inner loop j goes from 0 to I minus 1. Now for both the pairs I and j, we check if nums j is strictly less than nums I. If it is, it means nums I can potentially extend an increasing subsequence that was previously ending at nums j. So if that is the case, then the new dpi will be maximum of the current value and dp of j plus 1. This effectively means the longest increasing subsequence ending at nums I is either that we have already found, or it's the LIS ending at nums j plus nums I itself. And after the inner loop completes for a specific index I, we update our answer to reflect the maximum value across all dpi to get the length of the longest increasing subsequence. And once we are done with all the indices I, we will return our answer. And now the question is, can we do better? And the answer is yes. By using the binary search based approach, we can significantly improve the time complexity to O of n log n, making the solution more efficient, especially for the large arrays. This video is already quite detailed, so I'll cover this approach in the upcoming video. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.